Yeah, good morning and welcome to the 23rd online lecture. So, here today we will have a special tutorial. So, this special tutorial will mainly focus the questions that we witnessed in the internal exam. So, the first question there was something like this. Given that a source generates different symbols having varying probabilities, the probabilities were mentioned as zero point 0.5, zero point 0.03, zero point 0.1, and zero point 0.1. Let these symbols be represented by the unique code words as 0, 1, 0, 1, 1, 0, and 1, 1, and 1, respectively. That means there are four symbols with the probabilities as mentioned here. By using some of the encoding scheme, they were also assigned different code words as represented here. So 111 represents the fourth symbol having a probability of 0.1, and this first symbol, first code word represents the first symbol having a probability of 0.5 and so on in the same order. Now the question is, do you think the average code word length of these symbols is greater than the entropy of the source? Yes or no? You need to mention that. And based on your response here, yes or no, please justify your answer with numerical values. So in this context, the main part is here. You need to understand that whether the average code word length of these symbols, there are four symbols, is greater than the entropy. Is it yes or no? So to solve this, we need to have some theoretical knowledge. So the main concept need to remember is this: the average code word length L prime that will be greater than or equal to entropy, and it is smaller than or equal to entropy plus 1. So always you notice that entropy is the quantity having the lowest value, or it may be up to the average code word length, but entropy will never be greater than the average code word length. So you have the answer here for this. Based on this observation here, you have the reply here, yes or no, right? So always the entropy is less than or equal to the average code word length. And you need to justify that with the numerical values. So some inputs are given here, the probabilities and the code word lengths are given here. Using that, how do you establish this relation? That is the question actually. So we will try to solve that here. So the entropy we can find out using the equation probability and log of probability with a negative sign. So we have four symbols there having different probabilities: zero point 0.5, zero point 0.2, and zero point 0.1, and so on. When we substitute those values here in this equation, that is probability of the first symbol and log of its probability and so on, when you do this computation for all the four symbols, you should be getting a value around 1.685 bits. That is the entropy. Next, some more information is given in the question that those four symbols were represented by these code words. The first symbol is represented by this code word, second, third, and fourth symbol was represented by this code word, and so on. Now, with that, can we find the average code word length? That's equal to the length of the code word multiplied by the probability. This is a well-known equation. So for the first, there are four symbols. So for the first symbol, the average code word length is 1 because it has only one bit here, multiplied by its probability, maybe 0.5. For the second, the code word length here is 2, multiplied by its probability of the second symbol. Similarly, for the third one, we have the length as 3 bits, and it's a probability. You can go back and check in the previous page or in the given question. We have all the probabilities. You need to substitute that here and find the summation of these values. That should give you the average code word length L prime, like here. This is for the fourth symbol, its probability, and the code word length is 3 because we have 3 bits here. Altogether, you get around 1.7 bits. That's the average code word length. So, does this support the theory what we have seen in the very first point in the solution? L prime is greater than or equal to the entropy. Yes, but never less than the entropy. So that is what we can observe here. Yes, this is the relation we tested. Right now L prime is 1.7 and h of x, that's entropy, is 1.685. So this relation is well observed here and it is preserved because this is a theory. Now we will address the question, do you think the average code word length of these symbols is greater than the entropy of the source? Yes or no? Yes. The above numerical values justifies that. The average code word length is greater than the entropy, or it can be equal and never less than the entropy. So yes, the answer should be yes. And above numerical values, I mean, we have computed all these factors, L prime and h of x. So that is sufficient to prove this. Hence, it is proved. So this is the concluding remarks, or also called as QED. So that is important to end this answer. So this is how you can address the first problem or solve the first problem. Now let us move on to the next question. So in the second question, it was given that using the data given in the first question, do you have any recommendations to achieve the best possible efficiency of encoding? So from the first given question, you need to collect some inputs such as probability, maybe, or the code word length, etc. And then you need to recommend, do you have any recommendations to achieve the best possible efficiency of encoding? So the question here is to achieve the best efficiency. But there is a hint here how to achieve the best efficiency. Length of each code word be made better. So using this hint, how can we solve this part of the question? So from the given question, what information do we have? We have the entropy, average code word length, etc. In the first question, we can find out. With the help of that, can we find the efficiency? There should be an equation you might have studied. I am sure that you have studied how to find the efficiency of an encoding scheme. So we will first find the efficiency. The ideal value of efficiency is 100%. So can we do something better with respect to efficiency? That is what we have to uh, analyze here. To do that, one hint is try by varying the length of the code word, can we have a better efficiency? In that direction, we need to think. Okay, so we will try to address that here. So the first point here, we need to improve the efficiency that is given in the question, whether the present efficiency is the best or can we improve the efficiency. If you can improve the efficiency, how to improve the efficiency? By varying the code word length. Okay, from the given data, first we need to analyze what is the efficiency of the given question. The efficiency is equal to the average, the entropy divided by average code word length, h of x divided by L prime. That is the equation for entropy. So for the, I mean, from the given data, entropy, this is the direct substitution of equation. entropy divided by the average code word length. So that gives us the value of 0.991. That means 99.1% efficiency. So this is not the maximum. Maximum efficiency is 100, or the value here should be 1. Can we achieve that, or can we do something better than this? That is the question. Okay, we need to test it. So what is the intuition here? Let us vary the code word lengths. Then can we have a better efficiency? So when the code word lengths vary, the entropy or the average code word length also should vary, right? Accordingly, the efficiency also will vary. Okay, so we use this hint. We try to change the source symbol probabilities. That is, probability is equal to 2 power minus lk. So we know the probability is here. Probability 1 is equal to 0.5. Let us change the probability as 0.25. 3 as 0.125. Probability 4 as 0.125. Now recompute h of x and L prime for the new probabilities. That is, h of x in this case is equal to L prime. That is, you need to find h of x because you know the probabilities here. How did we get these probabilities? That is based on this equation. So we compute the new probabilities by considering the length of every symbol. Okay, for the first code word, the length is 1. So 2 power minus 1, that is 0.5. For the second code word, the length is 2. So it is 2 power minus 2, that is 1 by 4.25. For the third, it is 3. So it is 1 by 8.125. For the fourth one also, it is length is 3. So probability is 0.125. So these are the new probabilities we find here by considering the length factor. So when we have the new probabilities, we try to find out the new values of the entropy and also new average length of the code word using the same equation. We have seen it earlier, how to find L prime or how to find h of x. H of x is equal to minus pk log pk, or L prime is equal to the length of the code word multiplied by the probability. So using those equations, we find these new values, and then it appears that the entropy and average code word length all becomes equal. So efficiency is computed by the ratio of the entropy and average code word length. So in this case, again, efficiency of h of x by L prime, that is 1.75 divided by 1.75, that becomes 1. So that is the maximum value of efficiency we can attain. Okay, though this is the method of solving the second question, where you consider the lengths. So actually we consider the varying lengths and then find the new probabilities. So that is what in the hint, you consider the length, varying lengths, altering lengths, and then find a new probability. I mean, using that hint, you need to find out new probabilities, and using new probabilities, you find the new values of h of x and L prime, and that gives you a new value of efficiency, it is the maximum efficiency we can achieve. So this is how we find the efficiency value. Okay, the next part of the same question. Identify which among the three following codes are prefix free. Give reason. So there are three code word patterns are given. In the first one, you see here, second one, and third one. You need to identify which one, whether the first one, second one, or third one, which one is prefix free. We know the definition of a prefix free. So to say a code word is prefix free, it should follow the Kraft inequality. So that is given by this relation, summation of all code words 2 power minus lk. All this summed up should be less than or equal to maximum of 1. So here lk is the length of the code word. For instance, in this case, for the first case, all the code words have a length of 2 bits, right? So 2 power minus 2 plus 2 power minus 2, 2 power minus 2 plus 2 power minus 2. So when we sum up all those 4 terms, that can be 1 or less than 1. Then such a code word will exhibit this property of prefix free. Prefix free code words have an advantage that they can be easily decodable. Okay, the other way of finding the prefix free code is just comparing every code word with any other code word, and none of the other code word should be having a prefix starting with the code word which you consider for comparison. Okay, we will try all these methods. For instance, this is the general equation, Kraft inequality, that should be satisfied by all the code words. So we have seen that the first one has a, whether it satisfies this value. Okay, the second one, how to find out that? We need to substitute for the length of lk. For here, if you see 0, its length is 1. So it is 2 power minus 1 plus 2 power minus 2 plus 2 power minus 3 plus 2 power minus 3. Altogether, when you sum up, it should be less than or equal to 1. Similarly, for the third one, 2 power minus 1 plus 2 power minus 2 plus 2 power minus 3 plus 2 power minus 2. This way, you need to find out whether the code words are prefix free or not. This is one way, and also the other way is just comparing. For example, we go back here and see 0 0. Is it present entirely in any of the other code words? No. 0 1. No. 1 0. Whether it is 1 0 present somewhere here? No. 1 1. No. They are all unique. So they are all prefix. I mean, this is entire, all these 4 code words are prefix free. Second one, if we go and check whether 0 is present in any of the other code words at the beginning, no. 1 0, whether it is present anywhere here, no. 1 1 0, whether it is present in any of the other code words, no. Similarly, 1 is not present in any of the other code words. So it's also not, I mean, it is also prefix free. It satisfies the condition by comparing, I'm saying. Third one, 0, whether any zeros here, no. 1 0, any of these code words starting with 1 0, no. 1 1 0, anyone starting with 1 1 0, no. 1 1, anyone starting with 1 1, yes, here. This 1 1 is a prefix of this code word. So you can have here 1 1, and this 1 0 is here. I mean, here. So now there is a confusion whether it is 110 or it's a combination of 1 1 and this 0. So this is not prefix free, because 1 1, which is entirely another code word, it is present as a prefix of this particular code word. So it is not a prefix free code word. Anyway, we will check it with the help of Kraft inequality. So first, for the first case, the Kraft inequality is 2 power minus 2, 4 times addition, so, or multiply by 4 times, so that is equal to 1. Kraft inequality is satisfied. The second case, 2 power minus 1 plus 2 power minus 2. 2 power minus 3 plus 2 power minus 3, it's also 1. Third case, when you add up, it becomes more than 1. So this is not the condition for prefix free code. So third one is not a prefix free code from the craft inequality, or also by the method of comparison, what we have seen just before in the previous slide. We compared every code word, and we noticed that in the third code word, one code word was entirely present in another code word as a prefix, so that is not a prefix free code word, whereas the first one and the second one are prefix free code words. Okay, with the help of that, you can also try to build a tree diagram to represent it more meaningfully. That means your tree will start from one point. On the left hand side, you represent zeros. On the right hand side, you represent ones. And the tree continues at every node. For example, the code word may be 0, 0. Then you need to write 0 and then 0 and so on. This is we have seen. So that's a very simple method of representing the codes in a tree. So representing tree gives more meaningful. But in this question, that is optional. Okay, now we will move on to the next question. Do you agree that Huffman encoding is always unique? Yes or no? For a given probability of symbols, for example, probability is 0.37, or different probabilities are given here. There are 7 symbols and their different probabilities are mentioned here. Justify your opinion in detail. So the main question here is, there are some probabilities given for 7 different symbols. You need to use the Huffman encoding scheme. You know how to use the Huffman encoding scheme when the probabilities are given. And then you need to comment something here. Do you agree that Huffman encoding is always unique? So this we have discussed in the regular class. Whether the Huffman encoding is always unique need not be, right? Because in case of Huffman encoding, we will combine 2 symbols and put them in the next uh, column, or in next step. We will put a newly formed symbol at the top if there are 2 symbols having the equal probability value. This is also possible that the newly formed symbol can be placed at the bottom. By using these 2 schemes, when we do the coding will not be unique. The entropy can be unique, but coding cannot be unique, need not be unique. Sometimes may be unique, but not every time it is unique. So in this question, your understanding of that particular feature of Huffman encoding is tested. So I have asked here that part of the understanding, whether it is unique or not. Yes, it is not unique, right? So the answer is no. How to justify that? You need to solve this in one way, and also you need to solve it in the other way, that is placing the symbol at the bottom instead of at the top. Then you will come to know whether the coding schemes, what the coding values what you get, are they same. They are not same, they may not be same. So then you have the justification. Okay, we will try to solve that here. So this Huffman encoding, we have the different symbols arranged in the decreasing order of probabilities, and then we combine 2 code words of the lowest value, and we generate a new symbol here, or new probability value here. For example, 0.01 and 0.02, we add them, and the newly generated value is 0.03. And we represent the upper one as 0, the lower one as 1, right? And then we will sort them again here in the second step. This is the second step. We have sorted them again here. So the new candidate 0.03, that will be at the bottom of the list naturally. and we will proceed. So again, we have the two lowest symbols that are added here. So the newly formed value is 0.7, 0.07. So now we will move that value here. Again, there are other values, probability values coming from the previous step. The newly added value is 0.07. Also, there is one more value 0.07 from the previous step. So we have placed the newly generated probability value at the top of the list in the sorted list when there are two candidates having the same probability value. So this is what we normally do in case of Huffman encoding. Okay, we will continue. So now we have these two as the lowest probabilities, and we add them and generate a new value, that is 0.14, and again sort them. So of course this will be at the bottom of the list, and we will continue. We will again add these two values and generate a new symbol, new probability, that is 0.3. So again we have sorted that list and it is at the bottom here. And again in the next step we will add this and generate a new symbol, that is 0.63. So 0.63 will go to the top naturally because it is the highest valued element, and 0.37, which is in the previous step, will be carried forward here. This is again in the sorted order. Now we again combine these two and we get a value of 1, and that becomes the last step. There is nothing more to add. The top value is assigned 0 and the bottom value is assigned 1. Okay, now we know how to do the encoding. So we just need to backtrack from any point. For instance, x1, what's the encoded value of x1? So from here we just backtrack, that is 1 is the encode value for symbol x1. Similarly, for the other symbol, we can backtrack for any of these symbols. For example, x7, then what is the symbol, I mean what is the encoded value that comes in this way, like the pointer is moving? Yes, here. So the backtracked value is 0, 1, and 1, and again 1, and sorry, 1, 1, 0. Here not 1, it is 0, and then we come to 1 here, and again we come to 1 here. So this is the backtracked value for x7. Similarly, you can backtrack any of these values and find out what is the value for encoded value for any of these symbols, x1 to x7. So the list is given here. For example, x7, I mentioned 1, 1, 1, 0, 1, 1, and 0. Similarly, for x1, I mentioned as 1, and so on. The other values you can compute by yourself. Okay, this is one way, the normal way of doing the Huffman encoding. You are very familiar with this. Now, the question asks something else. We have to follow another approach. That is, when there are probabilities of equal values, then we will place the newly formed probability at the bottom, I mean at below in the next step, not at the top. Okay, we will do the same process here. In the first step, everything is sorted. We will combine these two and generate a new value here. Okay, in the next step, we will combine these two and generate a new value, that is 0.07. So 0.07 is a new value, and from the previous step also there is 0.07. So in this case, earlier we had placed this newly formed symbol at the top, and we had pushed the same valued symbol from the previous step at the bottom. Now we are doing the reverse. I mean, the newly formed symbol will be placed at the bottom itself, and this will be placed here itself. Okay, then we do the same process. There is no such instance after this. I mean, there is only one place we have to do the, uh, I mean, we witness the probability values having the same, uh, values having the same probabilities. So only at this point we have this confusion. So we will place it at the bottom. Okay, and we will finish the same process. And then we will backtrack and find out what is the encoded value for every symbol for this list. So in this case, the newly formed probabilities will be something like this. For instance, some of the probabilities they don't change. I mean, some of the code words they don't change. But at some places, because we placed that 0.07 at the bottom instead of at the top, as a result, some of the code words will differ by some small positions, minor changes compared to the previous encoding scheme. So in these two examples, these two instances of the same question shows that the Huffman encoding is not unique, need not be unique. In this case, it is not unique. So the answer here is no, it is not unique. The above numerical values justifies this argument. So we have two instances of the code words here. So that shows that it is not unique. So this is the answer. And then the next question, assist an information theorist to decide the best encoding scheme when there are 6 symbols to be encoded using Shannon's encoding, Shannon-Fano encoding, and Huffman encoding schemes. The probability of those 6 symbols are given here. And then further provide enough arguments to support your findings. So what's the meaning here? There are 6 symbols and their probabilities are given. So some information theorist has to decide if he uses Shannon coding or Shannon-Fano encoding or Huffman coding, what is the performance? Based on the performance, you have to give suitable recommendations or arguments to say which is better. See, in this question, this is an open-ended question. You can find out using these probabilities and using these three encoding schemes, you can find out the efficiency and say which is the best efficient scheme for this particular example. Or you can find the average code word length and say which is the best scheme. The efficiency, if you are finding, then the efficiency should be maximum. That which scheme gives that, that is the best one. In case if you're finding the average code word length, then the average code word length should be minimum. Then that is the best encoding scheme. So you choose anyone and suggest the information theorist which is the best encoding scheme. So that is what the question desires here. So first step, what do? We use one of the encoding scheme. Maybe we will use the Shannon's encoding. Since we know the probability values, we can use the Shannon's encoding scheme. You know how to use the Shannon's encoding scheme. Using that encoding scheme, we will find out different code words for those 6 symbols. In the second step, we will use the Shannon-Fano encoding, and also we find out the different code words for those symbols. Then we will use the Huffman encoding scheme and find out the different code words. Okay, right now we have all the code words ready with us. With the help of this, can we find out the efficiency? You know the equation for efficiency, maybe entropy divided by average code word length and so on. So for each of these schemes, you can find out the efficiency, and whichever gives the maximum efficiency, you can say that that is the best one. So in this question, it is not important that the numerical values you get, that is not so important. But your idea of solving this problem is more important. How do you decide an encoding scheme is better? Either based on its efficiency or based on its average code word length. So you should be able to give your opinion based on that. So since it's an open-ended question, uh, based on your idea of deciding which is better, either efficiency, so better, okay, or average code word length, so minimum is okay, that's also better. So uh, that is what the question uh, expects from you. Okay, then we will move on to the final question. So a source and its states are given, and the transition probability is also given. Show that in this scheme, the average information content in the message of length 1 and 2 are higher than the entropy of the source. So this is again a straightforward question. A source that emits different symbols are given here. A, B, C are the different symbol it emits, and it rests either in state 1 or in state 2. Now for this Markov state or state diagram, you need to find out the average information content. Generate is represented as G, G1 or G2 and so on. You need to find out those values, and also you have to find out the entropy, and you need to arrive at the general conclusion. We have a relation between entropy and GI values, G1 or G2 values. We just need to compare that. That is the question here. So, and also since there are only two states, the probability of the system in state 1 is half, or it is in state 2, it's also half. I have not mentioned that in the question because I left it for you to decide, because there are only two states. So you need to come to that conclusion if the information is not given explicitly, that each of the states will be having equal probability of 0.5. Okay, now first we solve this here. The question requires you to find G1 and G2 values and compare with the entropy. So we will do these steps. First one, we find the entropy of each state, state 1 or state 2. So we know the equation, general equation for entropy, probability log of 1 by probability. For state 1, how do we get to state 1? Either here or from here, right? We, in both the cases, we attain state 1, either from state 1 again getting state 1, or a transition from state 2 to state 1. So what are the probabilities here? That is 3 by 4 log 1 by 3 by 4 plus 1 by 4 log 1 by 4, 1 by 1 by 4. So many bits. Next, what is the entropy of state 2? That is, how do we get to state 2? Either from state 2 back to state 2, or a transition from state 1 to state 2. So those probability values are 3 by 4 and 1 by 4. So we substitute in this equation to get those values here. So it appears that both H1 and H2 are same here. Okay, with that we can find out the entropy, the final entropy. Final entropy is nothing but entropy of a state multiplied by the probability of, the transition probabilities. So H1 P1, H2 P2. So we know H1 values here, and probability of being in state 1 is half, or probability of being in state 2 is also half, because there are only two states. Probability of state 1 is equal to probability of state 2, that is half. So this value gives us the overall entropy as 0.8113 bits per symbol. Now we need to find out G values. G values, how to find G values, we need to just compute what are the different symbols we generate. When we say G1 value, that means generating any symbol having one letter, for example A or B or C. If you go back to see the previous slide, you will come to know how can we generate A. That is 3 by 4 multiplied by the probability of the state here. How can we generate A? Only here we can generate A, right? That is transition from 1 to 1. You have a symbol generated A, that is having a probability of 3 by 4, and it is generated from state 1. State 1's probability is also 1 by 2. So 1 by 2 multiplied by 3 by 4. Similarly, if you see B, how do we generate B? B is generated by the transition from 2 to 2. So 3 by 4 is a transition probability multiplied by state probability. State probability of state 2, that is 1 by 2. So that is what given here. Then how do we generate C? C can be generated by two ways, either transition from state 1 to state 2 or state 2 to state 1. The probability values are 1 by 4 in both the cases, transition probabilities. The probability of each of the state is 1 by 2, so that's why it is 2 by 8. So you can write a state diagram when you want to find the G2 values. That is from state 1 here. From state 1 we have either symbol A generated or symbol C generated. Yeah, from state 1 either A or C is generated with the following probabilities. And now when it is state 1, it generates symbol C, then it goes to state 2. From state 2 what happens? Either it can generate symbol C or it can generate symbol B. So this is basically written from the given figure. So that is how we write. You can write it any number of stages. But right now in this question, the first and second stages are sufficient for us. Only this part of the figure is sufficient for us. Okay, this is for the second state. From the second state, what transitions you have? Either it goes to state 1 or it goes to state 2. Yeah, we have seen from state 1 it can go to state 1 or state 2. State 2 it can go to state 1 or state 2. That's what we have seen here. That repeats here also. Okay, we just need two stages. Only this part of the figure is sufficient. So with the help of that we can find out G2 values. So to find out G2 value, for example, right now we'll find out G1 values. G1 is equal to 1 by n. N is 1 here. 3 by 8 log 1 by pi. Yeah, these values what we have found earlier, just substitution here in the equation of Gi. That is mi log 1 by mi. Okay, now going for G2. G2 means generating two symbols AA, AB, AC, BC, BD, CC, CA, and so on. So we have seen in the tree diagram how to generate AA. AA is transition probability multiplied by the state probability multiplied by again the transition probability of getting the next symbol. AC, this is the state probability multiplied by getting A, and this is for getting C. Similarly, all these symbols we can write from the tree diagram. CC, here there are two parts because both state 1 as well as state 2 can generate the symbol C, right? It is given in the tree diagram as well as in the given figure, you can notice easily. So that's why we have these values here. So with this help of these values, we can find out G2. G2 is equal to 1 by n. N is 2 here, and so many the value probability values of those symbols here in the previous slide we have seen. So that gives us G2 value. So now you need to compare G1, G2, and entropy values, and we can easily notice that G1 is greater than G2 or equal to H. So this is how we find out the uh, we will argue that this follows this relationship. This is what was asked in the question. So this is the end of this discussion, and we have learned how to address the questions. Mainly, these questions are from the previous first internal test. Okay, so this is the end of this lecture.